Oh, come now, I thought I had that fixed. The idea is we're going to do a u substitution backwards. Or we're going to undo someone else's u substitution that wasn't helpful. Like any substitution of variables, I need to calculate what happens to the differentials as well. So if an x is worth a sine of theta, then a dx is worth, well, derivative here is going to be cosine of theta d theta. Now let's put these into the formula for my integral and see what I get. So this now becomes the integral of the square root of 1 minus, this is an x squared, so that better be a sine squared of x. That looks pretty good, actually. And my dx is going to become a cosine of theta d theta. All right. So I still have this square root function, but I remember that cosine squared of x plus sine squared of x, or theta in this case, excuse me, is equal to 1. So I can just as easily write that 1 minus sine squared of theta equals cosine squared of theta. Hey, this is a very cool formula, very useful. That means that my integral is really the square root of the cosine squared of x, cosine of theta, excuse me, we did switch the theta variables. See, it happens to the best of us. Okay, now I've got the square root of a function squared. So that's going to give me the cosine of theta. And here's a cosine of theta, so let's call that cosine squared of theta d theta. And now this integral is one that I can solve, right? I'm going to use my technique from Friday. So the cosine squared of theta d theta, this is 1/2 of a 1 combined with a cosine of 2 theta. And what do I put here? It's got to be a plus. Because if I put a 0 in for theta, cosine of 0 is 1. So this would be 2 divided by 2. Looks good. D theta. So my antiderivative here is I'm going to have theta divided by 2 plus negative sine of 2 theta divided by 4 plus my constant of integration. Okay, well, my problem started in the variable x, so I want my answer to be in the variable x. Let me switch back to my x coordinates. A theta is worth an x. Let's figure this out in the next video.